I am thrilled to be joined by Mr. Eric Weinstein today on the What is Money show, where I think we're going to get into some very deep, fascinating, and potentially complicated topics. Eric, welcome to the show.
Robert, it is thrilling to be here. Always a little bit nerve-wracking because the Bitcoin community is seldom unopinionated, but it's a really interesting community with lots of voices that I think highly of. So this is going to be fun.
Well, I think there's a lot of opinions out there, especially in Bitcoin community. Instead of being strong opinions loosely held, they seem to be strong opinions strongly held. But I try to hold on a little bit more loosely myself. And so I hope that our conversation today can help shed some light on reality, as you said earlier. Certain groups of people, which I'm sure we'll get into, are very good at some things, but not so good at depicting reality. So similar to your show, I'm trying to get to the bottom of things. I think the avenue that I've chosen has been effective so far. Asking this question, what is money? And all of the twists and turns and the rabbit hole that takes you. But so where I thought we could start today is with this concept that you've worked on a lot and popularized in the Bitcoin community, which is gauge theory. And I'm still, I mentioned to you offline, I've read the chapter. This is in the book called The Physics of Wall Street, chapter 8 that you recommended. It discusses gauge theory.
By James Weatherall.
Yes. And it shed some light on the nature of gauge theory for me, particularly relating it to some other stuff I had read about quantum mechanics and whatnot. And interestingly, it's connected to path dependence, which I think is something that's very important in Bitcoin's emergence. So maybe we can get into that. I'm going to throw out a general definition and maybe we can just start to riff on it.
Sure.
Gauge theories use geometry to compare apparently incomparable quantities.
That's cool. That is the sort of what you're defining as something called parallel translation, which is the main way in which we are so far using gauge theory, although we have plans to, if this ever gets past the initial layer, there's quite a bit more you can do with gauge theory than parallel translation. But I think that what you've just defined is a concept called parallel translation, where I can say what it is fairly simply. There are lots of concepts of what it means to be constant. Oh, he's a constant in a changing world. That sort of an informal notion. In mathematics, one way in which we talk about constancy is we say that something has a derivative equal to zero. And if the derivative measures the rate of change and the rate of change is zero, then something by inference is constant. Now, it's very weird. We teach people all about differential calculus through, let's say, the second year of college, typically. And then we reserve a very advanced notion of differential calculus really for graduate school, for maybe 2 years later, and you have to decide that you're going to major in either mathematics or physics. And that's called covariant differentiation. Now, what is covariant differentiation? It's a concept whereby you not only have multiple functions that you can consider, but multiple derivatives that you can consider, not just one. Usually we have lots of different functions, but we only have one derivative. Take the derivative. And in fact, that turns out to be a very wrong notion, that you should, in fact, consider a world of different derivatives. That way, let's imagine that you rescale some of your y-axes of a function. If you rescale the derivatives at the same time, then assume that you had a constant function and then the function were scaled to become like an exponential. As long as you scaled the derivative to become in some ways like an exponential, it would continue to be viewed in the same way. That is, the new scaled function would be killed by the derivative, which is the new derivative. The scaled derivative would kill the scaled function in the same way that the ordinary derivative killed the original constant function. And so in a certain sense, covariant means that the derivative is varying along with the functions that it is meant to attack. So to take it all the way back up, if you don't even know calculus, derivatives measure rates of change.
Yep.
Something is constant if its derivative, that is its rate of change, is zero. It's not changing. But there are multiple different kinds of derivatives, and those are called covariant derivatives. And the covariant derivatives can vary along with the function, so that if one function was constant under one derivative, a new function would be constant under the new derivative if they're both scaled by the same factor. And that would be called gauge invariance or gauge covariance.
Okay. I'm going to try to echo some of this back to you and let me know where I'm wrong, please. Is this somewhat, and I should tell the audience, you and I met in Los Angeles. I had the first 2 cocktails I've had in 18 months with you, and it was a very enjoyable conversation overlooking the Los Angeles skyline, talking about...
You're telling it wrong. You and I checked into a hotel where Robert Plant famously said he was a golden god, and I think Jim Morrison hung off the ledge, and we got hammered in West Hollywood when you fell off the wagon. But go on.
Much better telling of the story. I did save some notes from that conversation, and I think the first point you're talking about here, for the audience that's visual, this is a small drawing of that. So essentially showing an exponential curve, but if the unit of measurement or the ruler is changing along with the curve, I guess effectively stretching out the unit of measurement, that can offset some of the change that's actually occurring.
Sure.
And I mapped this, my understanding, back to Wittgenstein's ruler. And he said that if you use a ruler to measure a table, but you can't trust the reliability of the ruler, you cannot be sure if you're measuring the table or you're measuring the ruler.
Beautiful.
So
it's really good.
So we need this. I mean, to reach consensus in the world, we need invariance, right? We need something that does not depend on interpersonal trust, but instead depends on some form of rigorous verification. And the one other thing I want to mention here is this concept of covariance. I mapped this onto inertial frames of reference. And I guess this is just in physics more generally, where, correct me where I'm wrong here, because I may be wrong. The special theory of relativity was special because it only applied to frames of reference that were moving in tandem.
And it really only applied in flat space.
Yes.
You could almost call it delicate relativity rather than special relativity, because it's fragile.
And then general relativity opened it up to, I guess, non-covariant, or I guess you could just say variant frames of reference. Is that correct?
Yeah. But if I can riff with you, if you don't mind.
Please.
General relativity opened up the idea that the rulers and protractors, that is the measurement devices, which Einstein would have called a Riemannian or a pseudo-Riemannian metric, just a fancy name for rulers and protractors, an ability to take lengths and angles. You can allow those to vary from place to place. Whereas in special relativity, once you've set the rulers and protractors at one point in space-time, every other point in space-time inherits the same rulers and protractors, only at that new point. So Einstein's, great insight 10 years after his famous, 1905 Annus Mirabilis, was to say, what if we allow the rulers and protractors to become dynamic and part of the system, and we feed back the information of the measuring devices and the measured. So the measurer and the measuree are in a dance with each other, which we call the Einstein field equation.
Right.
In this situation that we're talking about, it's weird because prices measure quantities. So the ruler of quantities that we would measure quantities by would be prices, right? Because if you buy 3 carrots from your supermarket to put into a salad, or you buy a 3-carat diamond is probably a lot smaller, but it's much more valuable. So the economic ruler tends to be the pricing system. On the other hand, if you want to measure the prices, then you're using a quantity ruler. Now, both your rulers are varying, right? Because your economy is creating different levels of output from moment to moment, and the prices are moving around. And so it's kind of a wonderfully diabolical situation in which the ruler of prices is goods, the ruler of goods is prices. Both rulers are moving around. And we call the measurement devices that allow us to measure each in terms of the other price and quantity indexes. Now, that's how we get CPI, which measures inflation, supposedly, and GDP. These are both price index numbers. And the other thing I would say is, if you want a very simple visual, if you go to the internet and you ask what's gauge theory, you get a bunch of stuff that's not understandable. And sometimes people get angry at me and they say, Eric, you're not understandable. But I think I'm actually more understandable than anybody almost when we have a very simple point. And I'll just say it. If you want to measure a derivative, you usually measure the rise instantaneously over the run. Yes. How far you go along my hand versus how much you go up towards the ceiling. That's the rise. This is the run. Gauge theory is simply saying you don't have a universal level. Think about a carpenter's level with that little bubble that floats around. This could be called horizontal, sloped up. This could be horizontal. There's no set concept of the reference level where you measure the rise from. That, in a nutshell, is all gauge theory is. This is ordinary calculus. There's only one reference level to measure the rise in rise over run. And this is gauge theory. And the idea being that if I scale a function, I have to scale the derivative at the same time, which means I have to change the level, which I call horizontal. So if I'm willing to change what I call horizontal, then in some sense, what I can keep doing is continue to take the new derivative of the new function, and it will equal the same transformation applied to the old derivative of the old function. And the reason that derivatives are so important, by the way, is that if you want to know how things propagate, how things move in the world, it used to be that we said that economics, in a sort of a bit of an off-color joke, had physics envy. And the fact is that physics lives on partial differential equations. It tells how things move across time and space. And if economics cared to continue the analogy with physics, it would be focused on its theory of derivatives, which we've now called gauge theory. And if you want to think about physical gauge theory, and this is going to be kind of a crazy statement, electrons are basically the functions and the photons are basically the derivatives. So quantum electrodynamics is the theory of electrons and photons in interaction. And it's really a theory of functions and their derivatives under a gauge principle that keeps everything together.
Okay. Lost me a little bit at the end there, but
well, let's go back to Bitcoin then.
Okay, please.
So how did all this crop up? This cropped up because, as in the book you read, which is The Physics of Wall Street, in the early 1990s, my collaborator and now wife and I, Pia Milani, started to suggest that all of economic theory is a naturally occurring gauge theory that had not been recognized. And what's more, the so-called marginal revolution, which was the penetration of differential calculus and associated thinking into economics, used the wrong notion of the calculus. It used the ordinary calculus that you would teach to a first or second year undergraduate who might be going on to, let's say, medical school. The right version of the calculus is only taught to differential geometers effectively and physicists or people who study either one of those two subjects, because it's not yet penetrating the world. But allow me to make a prediction on your show.
Please.
I predict that every serious client of the ordinary differential calculus will become a client of gauge theory within, say, 100 years. In other words, gauge theory is simply differential calculus done correctly. And what's more, it's backwards compatible. Anything you could do in the old differential calculus, you can do in gauge theory. And by calling it gauge theory, it definitely sexes it up a bit. It makes it seem like super exotic and fancy. But it's nothing more than differential calculus where rise over run is measured from a reference level that is set internally within the theory. So how did this all get going? Well, because economics is a major user of differential calculus through the so-called marginal revolution, we thought we had stumbled on a complete revolution within economics. Every single thing that differential calculus had touched was using the wrong version of the differential calculus. And if by happenstance that particular application was fine, you could retain it because it was 100% guaranteed backwards compatible, because this reference level is always included in the starter set. But it turned out that economics was making use of the actual geometry determined by these derivatives. So, famously, I think George W. Bush said that, or I forget who it was, we'd hoped we would be greeted as liberators in Iraq. I think we had hoped that economics was going to be really excited to see this. But in fact, what happened was that it complicated everything. Are you telling us that all of economics uses the wrong version of calculus? That the marginal revolution, which permeated every aspect of economic theory, is in effect using the wrong math? And the answer is yes, that's exactly what we're saying.
Wow. Okay. Let me try to echo some of this back and see where I get to. So the old view was that space-time was this fixed fabric, this theater on which everything played out in the cosmos. Einstein comes in, says it's not like that. There's actually a conformity between action and matter and energy and space-time, right? We know mass bends space and time, and acceleration changes the effects of space-time, et cetera, et cetera. And so the rise over run, which I guess is derivative.
Yeah.
Right. That's the first derivative. This is a ratio of movement across space and time. It's how we define movement, actually. It's even speed itself, right? It's change in position over change in time. I guess I'm saying that correctly. How quickly you move across space over a given amount of time. It's a ratio. To tie this to economics, prices are ratios of exchange expressed in money, which is just the universal language of economic numeracy. And that's done, I mean, it emerges naturally, but it's done as a cognitive expedient because it's a lot easier to talk about things and perform economic calculation. Actually, it's only possible to perform economic calculation in money versus trying to tell me how many tables a chair cost and, all the endless exchange ratios.
Yeah. When you tell an economist, that's like comparing apples and oranges, they say, so.
Exactly. And so that clearly points to the importance of money. And now just to speak to the marginal revolution of value, as I understand it, before, and this is in the 1870s, I think. So this is relatively new. Before the marginal revolution, there was a belief that individual objects had intrinsic value, or these units of utils. So there were a number of utils in a wagon, a number of utils in a house, and the actual trading value of those was some objective relationship between the two. Marginal revolution comes along and says, no, there is no cardinal number of utils or whatever these elementary particles of value are. All there actually is preference, right? Each market actor has preferences, ordinal preferences, not cardinal, meaning that you can't assign a number. You can't say this house is 100 and this wagon 70. It's all about this market actor prefers the house to this number of wagons. They have a rank ordered list of preferences. So it's an ordinal list instead of a cardinal list. And this was the subjective revolution, right? There is no objective value. It's all subjective to the market actor's preferences.
It's an interesting point. Economics refers to cardinal versus ordinal utility theory, as you state. And I think John Stuart Mill and company were associated with actually coming up with units, so real numbers to measure just how happy or sad something makes you. I forget whether it was Pareto or Marshall, but fairly early in the 20th century, there was a lot of pressure to drop this as an uninvestigated